little big data set, right? Today we are going to take the same big data set and try to understand hashing vectorizer, because in some cases you may get too many features from a character, no, from a text data set. When you are getting too many characters, either you may have to build a deep learning model, or you may have to reduce the dimensionality of the data set in order to perform or apply a machine learning algorithm. You may have to either reduce the dimensionality or you may have to go to the deep learning technique. So to reduce dimensionality, you may brutally eliminate some features, right? Maybe stop words kind of features you can eliminate. And maybe some features which are occurring very rarely, you can eliminate by looking at frequency distribution, you can eliminate, right? But those are maybe a little better way of doing the elimination is trying to create buckets by doing mathematical technique. So hashing vectorizer is a class, right? Like count vectorizer, hashing vectorizer is a class which does this. How does it do? It will calculate a hash code for each of the feature. How will it calculate? For like, if if it need to calculate the hash code, this is how it does. It took a primary prime number p, right, 13, right, and then it took the ASCII code of L, right. L's ASCII code is 108 into 13. I's ASCII code is 105 into 13 square, right. Case ASCII code is 107 into 13 to the power of 3, like that. So the formula I wrote is wrong here, right? P to the power of 1, P to the power of 2, P to the power of 3, like that I should be writing. So I wrote either way, some function, right? Some function which is calculating the value, and then you are taking mod of 1024. Is this 1024 constant? No. If I want to collapse the total data into 1024 maximum number of features, then I'll take 1024. If I want to collapse it into 512, I'll take this as 512. If I want to collapse it to 100, I'll take 100 here. Generally, it is 2 to the power of whatever. This is 2 to the power of 32, I think. Yeah, 2 to the power of 32, this is. 2 square, 2 cube is 8, 2 to the power of 4 is 16. To the power of 2 to the power of 4 is 16, to the power of 8. No, let us calculate. 2, where is it? X to the power of y where is this x to the power of 5? Oh my god, that's too big number, right? 2 to the power of 2 to the power of 8, okay, 16, 2 to the power of 16, what, 2 to the power of 10, I think 2 to the power of 10 it is, right? 2 to the power of 10 is the this 1024. So 1024 number of features will come. So here the hash is calculated like this. You take this equation, mod whatever the outcome is the let me write it down and explain a little bit here. I think you got the gist of it, but here, right, if you take x mod 5, you will get maximum 5 numbers only. Did you get this point? If you do x mod 5, you get only 5 numbers. Did you get this point?
Yes.
Yes. Yes.
Any questions there? No? Right? For the, if x is this one, right? If x is 1, 1 mod 5 is 1 only. 2 mod 5 is 2 only. 3 mod 5 is 3. 4 mod 5 is 4. 5 mod 5 is 0. 6 mod 5 is 1 again. 7 mod 5 is 2. 8 mod 5 is 3. Like that. So if these are the numbers, this is the number for some word, then you will get, ultimately after hashing vectorizer calculation, you get this number. Now, if this number is belonging to sum of this number, right, that whole calculation, then mod 5 is going to give you this number, right? Like that, if some number gets 8 again, that will get collapsed to 3. So two distinct words are getting collapsed as one number, and you are going to take the numbers, right? Here you got like, maybe you get some other thing also, maybe love, maybe prefer, right? I am actually taking syntactically, semantically similar words, but it may not happen like that, right? So it will actually consider 3 features as 54. If any of these comes, it will count here, right? All 3 are present, then it will be 3 count there. Right? Count vectorize only. We are calculating hashes for each of the feature instead of taking the words. So we are intentionally collapsing because there are too many features. This may work, right? This may work because if you have 1 billion features or 1 million features, 1 million words in your distinct words in your data set, the data set may become too sparse and the pattern may be distracted, right? Pattern may be like spread across the total the numerical representation. When the matrix is too sparse, right, the algorithm will face difficulty in understanding pattern. So when you shrink it, there is some pattern here in identifying the hash values. They may make sense, they may not make sense, but it will try to produce some result. So in some cases this works. I never used it, but in interviews, right, they'll ask if you have too many features, what you will do. Whether I'll go to deep learning. In my view, I'll go to deep learning, right? If somebody doesn't know deep learning, right, they'll ask this question and they'll ponder you till you answer this hashing vectorizer. So there are two ways. If you want to do only machine learning, then hashing vectorizer. If you want to do deep learning, then you can do whatever, right? It's going to be more sophisticated. Right? You got how the hashing vectorizer works, right?
Sir, one comment, sir.
Yeah.
So in the formula, you mentioned the first term, the P, and second term, P power 1.
Ah.
Uh, I think it should be P power 0, P power 1.
Yeah. I said that. No, actually, I should have said P power 1 here, P power 2 here.
Okay, sir.
This is n plus 1 I should have done.
Okay, sir.
Yeah. You can take that way also, P power 0, P power 1, and so on n. But here I should be, maybe 0, 1 like that. So anyway, I calculated like this, right? So I can change this one, right? Because ultimately, we are trying to collapse it to this many number of features. Okay. Yeah, that's a correction actually I have to make. I need to change.
Also, the last term it should be S n minus 1, not S n, because
If
n
it
is
is
the
0, maybe 1 n, sir.
no. I'm talking about
N
S.
minus
Yes.
1, yes, n minus 1, yes. There will be n minus 1 number of whatever, yes. Yeah. Maybe this is better because I already wrote this way, right? So this is better. Right? It doesn't matter. This way or that way, it doesn't matter. Ultimately, we are trying to reduce. Oh, maybe matters because the implementation, right? We are exactly trying to understand the implementation, that then it matters. But basically the logic here to generate this is this way. I definitely need to correct, I'll correct it. Okay. Okay, so how to build it? There is a hashing vectorizer class. The same way, right? Like in count vectorizer, we'll do this. So I have taken the actual data set, the train set. I did not took test set. And I took yesterday. I created the stem corpus, right? I took that stemmed corpus and I loaded it, right? And then I am doing fit transform on the hashing vectorizer, which will create a number of features. See this here, I took 2 to the power 16, right? Why did I got this many features? That's what I was worried about. So let me see. 2 to the power of 16, right? So that many maximum features you will get. Actually, how many features were there when we did 70,340? But when I collapsed, right, around 10,000 features actually merged into other features because of this whatever logic here. Got it? So this is the X now, and this is Y will not change. I fitted the model, I got 90% accuracy. Now if I see on the test set, I'll know whether the model is working good or not. Here it overfitted, right? It got 93 on the train set. On the test set, we have got 84. Right? When I do hashing vectorizer, on the train set, the accuracy reduced. You know, if the accuracy improves on test set, right, then it's going to be good. Right? This approach is going to be good. Okay. So this is hashing vectorizer. Yesterday itself I would have explained, but I don't have the code properly written. I corrected it now. So we are good, right? Can I move on?
So is that 10 to the, sorry, 2 to the power of something is a hyperparameter, sir?
Yeah, it's a hyperparameter. N features is the hyperparameter. How many features you want to extract ultimately, or how many features you want to collapse to? Right? That's what the feature is, parameter. This one I said I'm going to explain, right? N-gram, right? So in bagging, bagging model, or sorry, not bagging, continuous bag of words model, the count vectorizer. Let me take a screenshot here. So there are called as 1 gram, 2 gram, 3 gram models. Okay. So here, suppose that what is this movie, right? So I like a movie. This is the review. I like maybe latest movie. I don't know, right? I like
Crack.
huh?
Crack.
Crack. Okay. Terminator movie, right? Or Crack movie, Ravi Teja, right? Acted well, right? Acted very well in, right? Crack movie, right? These are the reviews. Suppose that these two are the reviews. So if I say 1 gram model, right? 1 comma 1, right? So let me try to show you the actual API and then come back. So again, we are going to talk about this n-gram models in language models. Right, see this, n-gram. Lower and upper boundaries of the range of n values for different word n-grams. So what that means is, if I say 1 comma 1, right, what will happen is the review 1, right, review 2. Now you are actually the count vectorizer is trying to convert that into numbers, right? So the words are going to be I like Terminator, right, and movie, and then Ravi, right, Ravi, and then acted, right, very, right, whatever, right. So like that it is. So it's going to be, this is 1 comma 1, right. When you say n-gram range is equal to 1 comma 1. So what will happen here? You know, you'll get 1 here, 1 here, 1 here, 1 here, 0 here, 0 here, 0 here, right? 0, 0, 0, 0, 1, 1, 1, whatever, right? So like that it is. 1 comma 1. If I say 1 comma 2, right? If I say 1 comma 2, minimum is 1 and maximum is 2. So then the data set will be converted like this. R1, R2, right? I right, like Terminator, right, Terminator movie, and then Ravi and Ravi Teja, and then Teja acted, right, like that it is. So now the features are going to be, I is one feature, I like is another feature, like is another feature, like the Terminator is another feature. Terminator is one, Terminator, you know, movies, right, and again movie, right, movie is another, right, like that. So these are 2 grams, bigrams these are. You got it? The consecutive, you know, consecutive words are also considered as features. And you know, if you say 1 comma 3 here, right, it will be like, you know, it will take I like Terminator also as a third feature, and then like Terminator movie as, you know, next 3 features. Then Terminator movie as next features. Like that it is. Got it? These are called as bigrams. Bigrams, these are. Okay. If you have 3, we call it as trigrams. If you have 4, 4 grams. 5, 5 grams, like that. Generally, bigram and trigram models work better because because you know, some of the cases, right, in some of the reviews you may get 2 words together and they make more sense than, you know, don't I don't like, or you know, don't like is a, you know, is a more appropriate thing to specify a negative review, right. If you take like and don't separately, it may not make that sense, but you know, if you take both together, right, it may make more sense, right. So in a numerical representation. Got it? N-gram range.
Yes.
Okay. So that is, you know, we'll talk about this again in a many, you know, in maybe in the language models. Okay.
But the number of features will increase, right, sir?
Yeah, number of features will definitely increase. And if you are using the hashing vectorizer, it may actually collapse and damage this also. Whatever the intention you try to create may get damaged. But if you say n-gram is equal to 1 comma 3 and then do hashing vectorizer, it may actually damage a little bit and it may create some patterns also. We don't know. It's all mathematical, right? So you need to experiment and see. You need to trial and error. Got it? Okay. So that's about the, you know, bag of words representation. And there is
So
another
one,
representation. Yeah, go ahead.
one doubt. So
Please.
dimensionality reduction, we have PCA also, right?
Yeah, yeah.
So okay, that will be applicable to this, or there is a limitation that we cannot use this PCA here.
See, PCA, basically PCA's intention is to extract the correlation within the features, right? In a text data set, there may be correlation, but the correlation may not be that strong, and the correlation may not be deciding the target variable, right?
Oh, okay, yeah. We find the covariance matrix there. Okay, yeah. Here,
You know,
yeah.
here, you can, when you apply PCA, right, it will anyway find out the covariance matrix, and there is one problem with that. There will be many features here, right? So there are 70,000 features. When you say covariance matrix, it's going to create 70,000 by 70,000 matrix, and on top of it, it's going to extract principal components and then multiply and all that. And that's going to be tedious, right, for the processor, and you need memory, huge amount of memory. And second problem is the PCA applied data may not perform well as the original one, because the correlation may not be the one which is having the most predictive power, because for each sentence and the other, there may be the words may be different. Got it? No, I love whatever. No, I prefer to watch whatever movie, and I like whatever movie. Right? The prefer and like are different, and right, movie may be common. But when you are actually trying to extract covariance, you may not get that much covariance from the data. Multicollinearity may be less in text data compared to numerical or other kinds of data. Got it?
Yeah, and also here here it is like 1010, right? Maybe that
Yeah.
may we may
Matrix is
losing the
also
essence also.
matrix is also sparse matrix. We call it as matrix is dense or
Yes,
sparse,
yes,
right? Sparse matrix, then you may it may lose essence also, right? So it may lose essence in the sense that essence may not be useful in making proper predictions. So that's where, right, on the text data, we try to apply naive Bayes, because naive Bayes assumes there is independence between the features, and it is close, right? In a text data, the independence is going to be there, especially when you are taking the syntactic representation, like bag of words and TF-IDF kind of representations. The, the independence is going to be there. Now, compared to the numerical other data sets, in text data, the independence is going to be more between features. So that's where you take naive Bayes, it may work better, because naive Bayes already assumes independence. Got it?
yeah. Thanks.
So yeah, that's the way you to think actually. That's a good question, and that's the way to think. Say, can I apply PCA? Right? Can I apply kernel SVM? Can I apply SVM? What happens, right? This is what you need to experiment with the data, right? You try to experiment, right? Apply PCA and then take the output. Maybe 70,000 features are there. You apply PCA, maybe 100 features you take and try to build a model. See what happens. Or you try to do that experimentation we did on the PCA class. That how many features will be extracting 99% of the variance in the data, right? Explain variance ratio, right? You put 0.99 in the PCA, right? N components is equal to 0.99. Apply the model, see how many features are coming, and then take those features and try to build a model and see how much accuracy you are getting. And this is going to give you the clarity on the theoretical understanding and practical, whatever. Right? Definitely need to practice on this data set and anomaly detection, the fraud detection. If you practice these two, right, you will get clarity on where to use which algorithm and how to handle the most complex imbalanced data sets and in the classification side. Okay, so that is about the bag of words representation. Now, right, we are going to move into a little more complex one called as TF-IDF representation, term frequency inverse document frequency. That is also syntactic representation only, but it's a little more intelligent thing, right? When we started looking into bag of words, I said that the stop words, right? Stop words may add noise to the data, right? Add noise to the data in a way that the counts for the stop words, the cells which are related to the stop words are going to be more. And when you build a model, they may get focused more when compared to the most important words in the text. Can we do mathematically? Can we reduce the importance of those static, stop words mathematically? That's the question we are going to answer with the TF-IDF. Got it? We are trying to understand another way to represent data, numerically represent data. We have seen bag of words. We are trying to see another way to represent numerically the data, that is called as term frequency inverse document frequency. The advantage or the difference between the bag of words and TF-IDF is TF-IDF tries to reduce most occurring words, the calculated value, to low. Right? In bag of words, most occurring words are getting high number in the cells. Right? Do you agree? Most occurring words are getting big number in the cells. Right? Do you agree
Yes.
with my? Right, in the TF-IDF, right, it will mathematically automatically it will try to produce numbers in such a way that most frequent words will get low numbers, moderately frequent numbers will get high numbers, least frequent words also get low number. Least frequent and most frequent will get low numbers, moderately frequent ones will get high number. The expectation or the understanding is that in any document, the most important words will be moderately occurring. They may not be occurring too many times, or they may not be occurring very less number of times. So if I write an article about artificial intelligence, it may contain maybe 4 or 5 places, the artificial intelligence word, right? But phrase, right? But if somebody is trying to create a spam artificial intelligence document that gets, when somebody types, right, artificial intelligence, if I want to get that as a first page in Google, um, I may write artificial intelligence 100 times, but the document may not make any sense, right? Just write 4 or 5 words and artificial intelligence, six words again artificial intelligence. If write like that, right? So it may not make any sense, right? So the Google should not pick those. That means most occurring words are not the important words. The essence is more important. But Google is not doing that. Google is going to look into semantic and syntactic, all kinds of reference, all kinds of inferences there. But TF-IDF is one way to represent data so that the data, the numerical representation is more appropriate. More appropriate in the sense, moderately occurring data will get a higher score. Okay, where is that? Where is 34? Do you see 34 anywhere? Yeah, this is all. I think I should put these slides into slides folder. Okay, so we are trying to cover two concepts here. One, right, I said TF-IDF, a numerical representation that reduces the most and least occurring words frequency is low. That is one thing. The second thing is how Google is working. If I say data science training in Hyderabad, right? What it does, it actually showing ads, right? That's a Google does lots of business on this, and we actually spent a lot of money, and to frankly speak, right, Google does lots of I don't know. These guys actually are not fair as we think.
Fraud?
Sorry.
Are they doing fraud?
Yeah, kind of. When I say kind of, right, we kept money for like around 6 to 8 months for ads, Google ads, and then I couldn't see much results there because we had to spend money in lakhs, right? If you spend in thousands, right? Maybe around 25 to 40,000 we spent for some months. It is not appearing like this, right? So I said it's not going to be good and take out the money, right? We are not going to do Google ads. Suddenly what they did is, if you type Google Datajango, right, Datajango like this, right? It was not appearing like this here. They took out, they invalidated the website. And not the website. There's a Google Sites registration. They invalidated it for no reason. They invalidated it. Again, we paid, right? We actually I kept even now I spend 3,000 every month, not to get ads like this, just to keep this active. If I'm worried that if I take that money out, right, they will make my page invalidated again. Okay, so that's one thing. And these ads they show, and these high rated ones also, right? They actually kind of some kind of goof up. It is not real. And one more thing I will tell you, in YouTube, there is YouTube marketing also. We kept a video there, and I kept a budget of 25,000 per month for that month, and all 25,000 got spent. Per click they will charge something, right? We have got around 24,000 review to 24,000 views, but nobody contacted. Even Facebook is also like that. If you put some Facebook ad there and put some money, right, these uneducated people will be clicking on it. You can actually funnel it to using some conditions like graduate and all that. They'll show this ad to people where people will be clicking it, right? Some people will have kind of a disorder, right? When as soon as they see something, they'll click it, right? They'll have that I think they'll have that analytics there. And then, these engines whatever are there, they'll actually post this ad to the people who click it, right? If you send me something, right, I'll not click anything. I'll just watch, right? And if I see it is really important, then only I'll click. Some people are not like that. They'll just click, and only that thing they'll do whole day, right? So those kinds of people they'll send, and the money will be deducted. So why am I telling you this is, these Google ad and YouTube ads and Facebook ads are for big companies, not for small companies. That's one thing, right? The point here I am trying to make is, when you try to type this, it actually brought these results from billions of scraped data. Do you agree that? Agree with that statement? Billions of scraped data, right? Do you agree?
Yes, sir.
Right. So it should have some way to find out the relationship between this string and the text contained in the website, right? In these websites, right, there will be some text, right? That text and this particular string should have relationship, right? We have to find that relationship. Finding that relationship and bringing out the appropriate documents related to this string is called as information retrieval. In information retrieval, TF-IDF is one of the representations. Term frequency and inverse document frequency is one of the representations which will help you find out the relationship between this particular string and the document. Okay, so that part we'll understand. So natural language processing is to convert your text into numbers where machine learning and deep learning can use. Information retrieval is another concept which is called as web mining, right? Web data mining, which will try to pull out the appropriate document. It's called document search, right? Image search, document search, these are all AI problems. Okay, and the concept is related, actually presented in information retrieval. Okay, so we are going to understand the information retrieval concepts along with TF-IDF. Okay, got it? So leave about that Google, YouTube, and Facebook's fraud. But no, the concept we are trying to cover is document search. Okay, information retrieval. Got it? So why are we going into information retrieval from NLP? That's the point I am trying to connect and explain. Okay, got it, right? I'm moving on. Okay, so there is huge volume of data, that is unstructured, and then the explored data is very little. And even if you look at Google, right? If your page, somebody typed something like this, and if your page falls into second page, you are gone, right? Nobody will look at it. And only first page people will look mostly. Maybe rarely they look at second page, and third page and beyond. No way that you will be, you will be visible to the world. Okay, so that's how it is, right? So information retrieval is a very important thing in organizations also. In one of our students company, they are actually trying to build a web application that will try to pull out RFPs, right? Request for proposal, RFP documents based on text search. Okay, so that kind of problem, if you have to solve, these concepts you need to understand. That's where I kind of introduced this information retrieval. So information retrieval is very important, and it is called as data mining or web mining also. And to do information retrieval, we actually have to represent data, right, in numerical format. So there are different numerical formats that can be used, and we'll start from the beginning, right? Start from the beginning and then understand the problems with it and come to TF-IDF. Okay, do we need to understand these? Maybe, may not be, right? But as a theoretical thing, right? It is better to understand. So there are different ways of representing your text for web mining or information retrieval. Term document indices matrix is one way. Second way is inverted index is another way, right? Third one is byword index is another way, right? And then we will come to the TF-IDF representation, right? In between, right, we will try to understand how to do web mining. Spelling correction is also comes under web mining. Spelling correction, right? If you go to Google, right, if I say right, see, I typed something wrong here. IMPRTNET, right? Important. I wanted to type right. I wanted to type important, right? I typed AT, right? Some mistake, but it actually found, right, AT&T. Right? See that? It is actually showing the correct spelling there, right? So that is what is it doing? Actually, it is trying to find out the closest match, syntactic closest match, right? It is not, it doesn't know whether the word is correct or not, first thing. So it is trying to find syntactic closest match in the dictionary or the database and trying to show those, right? See that here? Trying to show those, right? That is information retrieval. So we'll see that also as part of IR. So let us look at the term document matrix. See this here? I have taken terms as part of one of the definitions I explained you. Difference between token and term. Do you remember? What is token? What is term? What is token and what is term? Do you remember?
Token is something already defined.
Root word, right? Root word is the term, and token is the word from the data, right? You do the so white space tokenizer or word punct tokenizer. You use it and tokenize it, right? All these are tokens. But if you have terms and term, right? Sorry, the friends and friend. Friend is going to be the token. Friends and friend both are going to be, sorry, friends and friend are going to be tokens, and friend is going to be term. The root word is going to be term. Okay, unique root word is going to be a term. So term document frequency matrix is like this. All the words here are terms, and documents are the columns. Did we represent like this in bag of words? In bag of words, did we took words as columns and documents as or terms as columns and documents as rows, or this way we represent it?
Reverse.
The other
Reverse,
way.
right? In the bag of words representation, we took words as columns and documents as rows. But in information retrieval books and theory, they'll represent like this. Okay, there is a reason for this. But don't get confused. In our AI, our representation is all going to be words as columns, documents as rows, or terms as columns and documents as rows. For information retrieval concepts, the presentation is like this. Okay, don't get confused. Okay, remember bag of words representation only. This is just for information retrieval theory. Okay, so documents as columns and words as rows it will take, and it will try to put the term document indices matrix will not put count here. It is just that whether the word is present in the document or not. Right, word 1 is not present in document 0. Word 1 is present in document 1. We don't know how many times. It is just that a Boolean expression it is. It is there or not. Okay, that is called as term document indices matrix. Right? It's a Boolean expression. If we want to extract, right? If you want to extract a newspaper, right, looking for Gandhi and Mandela, but not containing Luther King, right? So you took many newspapers, right, documents, and then extracted tokens, Gandhi, Mandela, Luther King, right, all these, politicians or, freedom fighters you took, and then you are trying to look for a newspaper which is having Gandhi and Mandela, but not Luther King, right? How to write an expression to bring out those documents using this kind of a numerical representation? That's the question I'm trying to answer. Okay, so these are the newspapers. Newspaper document 1, document 2, document 3. They're all columns. Tokens, sorry, terms are the rows. And Gandhi is present in newspaper 2. How many times we don't know. But newspaper 1, no. Newspaper 3, no. No, all these no. Right? Nehru was present there. Luther King is present there in these. Mandela was present. So if you want to find out, this is the query. A newspaper contains Gandhi and Mandela, but not Luther. That's the query. Okay. So to do that query, what you need to take is, you take this Boolean array and take this Boolean array belonging to Luther, take the Boolean array belonging to Mandela, do an AND operation. So you apply not onto Luther, right? You took Gandhi's Boolean array, Luther's Boolean array by applying not. When you apply not, right, all zeros will become 1, all ones will become 0. And then Mandela you take, right, you directly apply AND condition. If you apply AND condition on these three, it will become 0. It will 1. This is 0. This is 0. At least all should be 1. Then only it will be 1. Right. So second place you got 1. That means the second newspaper has got reference of all these three guys. That's how you can use. Term document indices matrix is a Boolean expression, and you need to write Boolean queries. You call it as Boolean retrieval model. This is called as Boolean retrieval model. You need to write, Gandhi and Mandela and not and not. It's not but. It is and not Luther King, right? So then you will take the arrays belonging to Gandhi, Mandela, and Luther, apply not to Luther, and then do a Boolean operation on that, and wherever you get 1 in that document, the presence is going to be there. And you cannot write all expressions. using this Boolean thing. And even if you can write, it is going to be very difficult to write. The Alta Vista, I don't know whether you know about it. It's a search engine. Alta Vista is based on this kind of representation. Okay, so we are trying to understand how Google is working a little bit. Okay, it's not exactly how Google is working, but by the time we finish this information retrieval, right, you will have a little bit of idea on how Google is working. If you have to build something like this in your organization, these concepts will be useful. And NLP and information retrieval are very tightly coupled. We should know both. Any questions here on Boolean retrieval model? Okay, so Boolean queries return too many or too few results. That's a problem with it. Requires a lot of skill in building query. You have to write this query very carefully, rather the retrieval model will not understand. Okay, you should almost write like a code kind of the Boolean expression. If conditions will have Boolean expressions, right? Those kinds of expressions you should write. And the document is either matched to the query or not at all. Right? See this? Even though there is Mandela was not, so Luther was not there and Mandela was there, only Gandhi was not there. Maybe this is a little more appropriate. In Google, if you type a query like this, right, it will actually show the newspaper 2 as the first document, newspaper 1 as the second document, newspaper 3 as the third document. Okay, but if you use Boolean retrieval model, right, only one newspaper 2 will come as a result. Got it? Did you get the problem with Boolean retrieval model? You will get either complete match or no match. That's it. Sometimes you may get 0 results. But Google, right, when you type any query, right, you copy your error and paste it in the Google, it will try to show at least 4 or 5 documents. Right? So give me one second. Yeah. So that's like Boolean retrieval model's problem. Got it? So this representation is not right. That's what the point I am trying to make. Right? Is there a better way? Right? The term document indices matrix occupies a lot of memory also. There is another problem with this. So if you have 1 million newspapers, right, around 500,000 distinct words, right, then the matrix would be 1 million into 500,000 cells. Right? What is the matrix dimensionality? This matrix dimensionality is what? Words by newspapers dimensionality, right? 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5, 6. 5 by 6 matrix it is, right? If you have 1 million documents and 500,000 distinct words, it is going to be 500,000 by 1 million. That many cells you will get. If each cell is a integer variable, right? Each integer variable is going to occupy 8 bits, right? Let me try to calculate that. How much space it's going to occupy. The term document indices matrix for Boolean retrieval model is going to occupy, if you have 500,000 distinct words, 500,000, right, and distinct words into 1 million, right, 110, right, into 8. This many cells it is going to be, that many bits it is going to be, divided by, if you have to convert it to bytes, 8, right, this many bytes divided by 1024 is going to be megabytes, divided by 1024 is going to be gigabytes, right? Is that right? Is my calculation right?
First KB and then MB, sir.
KB, MB. This is MB divided by 1024 is going to be GB. It's going to occupy almost 500 GB for 1 million documents. If it has 500,000 distinct words, it's going to occupy distinct tokens. Okay, sorry, distinct terms. Sorry, I am getting confused. distinct terms, then it's going to occupy 500 GB space, right? If Google need to build a Boolean retrieval model, you can imagine how much space they should need. Already they are having they are using lots of space to build these indexed documents, and they use their business to actually put these documents in front. It is not really it is not really for all things. It is not going to do appropriate Google search, right? Appropriate search. It is going to be how much money they are earning also they'll see along with the search. That's how they show these results. Okay, so in reality Google may not need this much of space if for most of the business related stuff. Okay, for maybe some cases, like if you are trying to look at errors of your code and all that, right, then it need to look into. So they may build different index and tables in I hope I imagine, right, they build different data structures for different kinds of queries. If it is business related, it gets diverted to a business point of view database. If it is not business related, it is general, then it will go to a general database kind of a thing. Got it? Right. So this is like it's going to occupy too much space, right? And then record only possesses one positions of inverted index. Yeah. So there is another representation called as inverted index that is like this. Instead of taking the documents, all documents and all terms, you take terms, right? This is called as dictionary. This is not your our English dictionary. It is the dictionary of all the terms. Okay, all the terms, right? All the bunch of terms collected from the corpus are called as dictionary. And this is terminology used in information retrieval. So I just from around 4 or 5 pages of text, right, I kind of created this diagram. So this is called as postings list. And Gandhi is present in newspaper 2. The Nehru is present in newspaper 2 and 3. Lothar is present in 3. So wherever the term is present, only those array lists will take, right? Array lists will take, or lists will take, and then point. It's like dictionary of lists. The key is going to be the term, the value is going to be list. Key term value list, key term value list, like kind of structure it is going to be, right? Inverted index we call it as. It occupies only 0.2% of whatever, wherever the one is there, it's going to occupy that. So in this term document indices matrix, right, it is a sparse matrix. Most of the data is going to be zeros. Very rarely you will have ones, right? Only 0.2% of the places you will have ones. Out of those total 500,000 by 1 million, you will have only 0.2%, right? So that much space this inverted index will occupy. But there is another problem with this inverted index also. To build this inverted index, you will follow like this. Collect the data, right? These are all the tokens, right? And then tokenize it, right? Those are the tokens. You take this as the document, you tokenize it, you got tokens, and use a linguistic model to find out the root words or the terms, right? And then index the documents like this, right? That is called as inverted index. Term document matrix is occupying too much space. We came down to inverted index. It saved the space problem, but still it will have, I wanted to look for a sentence like, Gandhi met Mandela in South Africa, where Luther King is already present. Right? Gandhi met Mandela in South Africa, where Luther King is already present in South Africa. So the order is like this: Gandhi went there, Mandela and Luther King are already present in the South Africa country. Right? That order cannot be found here. Right? You know that Gandhi is there in a newspaper, Luther is there in another paper, Mandela is there in another paper, but you don't know whether all three came in an order or not. Gandhi in the text, Gandhi should come first, and then the Luther and so Mandela and Luther should come, right? So that order is not maintained in this. Okay, so inverted index has got that problem. The document count in which the term is present, right? Document frequency can be calculated. Based on the document frequency, we can optimize end and R queries, where we have used the query like this, right? We can optimize that. But position of the term in the document is unknown, right? Counts of the terms in the document are also unknown. So you know that a document in a particular document a person occurred, but how many times you don't know, right? To actually solve that problem, there is a I think this one, right? The positional index, positional
Please
indexing.
go ahead, sir. Go up a bit. Go up a
Positional
bit.
indexing is the solution, right? So here,
Sir, go up a bit, sir.
sorry, zoom. Okay.
No, go up a bit.
Okay.
So this red content, the disadvantages or the problems, is about inverse document or it's term document?
Inverted index document. Even term document also, term indices matrix also has got these problems, right? Inverted index is solving only memory issue of the term document indices matrix.
Okay.
Right? Rest of the two, these two are present in that
Both.
term document indices matrix also. We are trying to find a solution for this using positional indexing. Right? Positional index we call it as. Positional index actually takes a where the in which document the term is present and where all it occurred at third place, fifth place, and ninth place. Right? The word count, word index it is. If there are 10 words in the document, third word is Gandhi, fifth word is Gandhi, and ninth word is Gandhi, like that. Okay, and Luther also. Right now, whether if you look at the best document that may contain the sentence Luther met Gandhi is newspaper 2. Luther met Gandhi, because in newspaper 2 Luther is there, Gandhi is there, but the Luther occurred at 1 and Gandhi occurred at 3. That means there is another word in between 1 and 3. That may be met, right? That may be some other word also, right? But that may be met. Most probably the newspaper 2 can be the results outcome. Okay, this positional indexing has got a better solution, better data representation compared to inverted index and document term matrix. This is actually evolution of data representation. Okay, we are trying to understand evolution of data representation, because in future you may think this is the best way to represent documents and you may start coding, right? So if you know the advantages and disadvantages of representation, you will focus on what is there, right? So we are going to move to TF-IDF. This is also not the best representation. We will move to term frequency and inverse document frequency. So these are the basic representations which were present, which were used initially, right? Where Alta Vista, time based data representations. Then Google came in and they actually came up with TF-IDF and word vector representations and word searches, semantic similarity searches and all that. Okay, we'll see that. We will see those. But this is about data representation. Okay, there is one more point before I stop today's class, right? I wanted to explain one more point. So if you have to, if this is the representation, this is inverted index is the representation. If you want to see Gandhi, if you want to find out um, a document that contains Gandhi and Luther, suppose that there is a query that wants to see a document that contains Gandhi and Luther, right? What you should be doing is you should take all the newspapers that has Gandhi, right, and then take this newspaper and see in this list do we have it. In this list, do we have it? In this list, do we have it? In this list, do we have it? Sequentially, you need to search. Right? If there are n number of documents in this, you need to search n documents. Again n, again n. If there are n, m number of documents, m into n number of times, you need to search. N into m number of documents you need to search. Right? To avoid or to make the search more efficient, there is a representation called as a skip pointer representation. Okay, so you have ID, right? Document ID 2, right? From document ID 2, there is a skip pointer to 14. There is a skip pointer to 41. There is skip pointer to something else. In the second inverted index also, there is a skip pointer from 1 to 12, 12 to 35, like this. Now, you know that Gandhi is present in document 2, right? Gandhi is present in document 2. You come to second list and see what is the first document ID. This is 1. And go to skip pointer and see what is the ID of the skip pointer document. That is 12. Is 2 between 1 and 12? Yes. That means if the document 2 present in second list, it will be present in here only. If I search this space, that is enough. No need to search through all the data. Skip pointer representation reduces the search space. Do you got it? I wanted to see a document that contains Gandhi and Luther. Gandhi's the inverted index is this one, and Luther's inverted index is this one. If doc 2 is present in both the places, that means Gandhi and Luther both are present in document 2. That point is clear? Yes, that point is clear.
So
Yes, sir.
how these document 2, 9, 14 and document 1 to 7 are taken?
Like this is the list.
Okay.
This is, I actually may have to take the same numbers, but I have taken something else there. Right?
Okay.
Right? This inverted index is already there with you. Right? Suppose that the inverted index is already built. Now you are trying to see whether Gandhi and Luther are present in a particular newspaper. What you need to do? First, you need to take one term, see where all it is present, take that list and take the first document, see whether that document is present in the second list or not, right?
Yes, yes.
Right? If it is there, that means Gandhi and Luther both are present in that. Right? No, if it is not there. Second, take the second document, search in the second list, see whether that document is present or not. Right? If it is there, both are going to be there in that document. If not, again you have to go, or finally you have to find out all the documents that has Gandhi and Luther. You need to take all the n number of documents and search through the other list. Got it?
Yes, yes.
Right? Instead of doing that whole search, if you have skip pointers like this, you can reduce the space, search space. See, the ID is same, right? Document ID will not change. Whether it is Luther or Gandhi, document ID is same, right? Do you agree?
Yes, yes.
Right? Unique IDs they are, right? So now document 2 contains Gandhi. If I have to see whether Luther and Gandhi both are present in document 2, I should take the list of documents where Luther is present and take the first ID, first document ID, and skip pointer the second document ID 1 and 12. 2 is going to be in between 1 and 12. I will be searching here. No, if it is 2 is not there, right? Suppose that it is 25. Right, you are looking for 25 document, right? I will take the first document ID, it is less than 25. Second, skip and look at the document ID, it is 12, it is also less than. Skip and see, it is greater than. So I will look into this space. Do we have 25 here? No, that means 25 is not the resultant document. No, in the search result, you will show second document, but not the 25th document. Neither 9, neither 14, because they are not present. But instead of searching through all the space, you looked into only a particular part of it. So search space you are reducing. So skip pointers will help you reduce. This is I kept this because logically it's a very intelligent design, right? So why am I trying to show these is if you have to build the Google kind of systems or information retrieval systems, you may have to think about the data structures like these, right? Do a data scientist need to understand data structures? Yes, I would say, but it depends on the project. Okay, very rarely you will get these kinds of projects. Got it? Got it?
Yes, yes, sir. Good.
The course's intention is not just to explain you the concepts and code. I'm actually trying to show you, different kinds of problems in the industry and the way we need to think and the way we need to keep ourselves open, right? So that's it for today, and